I would like to now introduce what we call the Pythagorean identities of trig functions. The first thing I'm going to do is I'm actually going to derive the formula for the first one. So what I want you to do is I want you to first consider this true statement. We know that x squared plus y squared is equal r squared. Because the x, the y, and the r are sides of a triangle, we know that r will never be 0. And so what I'm going to do is I'm going to take each one of these three terms and I'm going to divide by r squared. Just follow me a little bit for this. What I will eventually do is I will derive a formula that has trig functions in it. So my plan is I'm going to start by dividing each term by r squared. Now, what that does for me is it creates three different ratios. The first thing I'm going to do is for the first ratio, I have x squared divided by r squared. Because both of them are squared, I can rewrite that as x divided by r squared. The same thing for the second term. Both the y and the r are squared, so I can separate it and I can say this is the same thing as y over r squared. On the right-hand side, r squared over r squared simplifies to 1. Now, for sake of the way that the formulas are written in the book, I'm going to interchange the first and the second term. I'm just going to rewrite them. Okay, we have y over r squared plus x over r squared equaling 1. Now, y over r and x over r ought to be familiar ratios based on trig functions. Y over r is the definition for sine of theta. So I'm going to substitute the trig function, sine of theta squared, plus x over r is the definition for cosine of theta. And then I have this is equal to 1. Now, in trig, instead of combining a trig function together using parentheses and squaring that, what we do is we rewrite the square directly after the sine but before the theta. So in other words, sine quantity squared is the same thing as sine squared of theta. And the same thing over here for cosine. Now, this is the first of 3 Pythagorean identities for my trig functions. So in other words, here I've established an identity that sine squared plus cosine squared is always equal to 1. So I'm going to call this my Pythagorean identity number 1. Now, the other 2 can be proven in a similar way, but for sake of time, I'm going to just state the other 2. Okay, so Pythagorean identity number 2 states that 1 plus tangent squared is equal to secant squared. And then Pythagorean identity number 3 states that 1 plus cotangent squared of theta equals cosecant squared of theta. Now these 3 identities that I have right here need to be memorized. We will use these over and over this semester, so make sure that you memorize these 3 things. Now, when you memorize them, make sure that you know that the trig functions must be squared. In other words, if I see a part of a problem and it says 1 plus tangent, and the tangent is not squared, then it's not equivalent to secant squared. The only way these identities work are if my trig functions are squared. I would like to do several problems involving these 3 identities. Okay, what I will say here is I will say I want to simplify, and I'll show you what is okay, and I will show you what is not okay. All right, on here, first of all, let's say that we have 5 sine squared theta plus 5 cosine squared theta. The 5's in the front are acting like constants. Because both of these two terms have a 5 in common, we can factor a 5 out. And so we have 5 sine squared theta plus cosine squared theta. From up above, one of our identities says that if you have sine squared of theta plus cosine squared of theta, that whole thing is equal to 1. And so I have 5 times 1, and so the answer here would reduce to 5. Okay, as another example, let's say that you have something along the lines of cosecant squared theta minus 1. Well, this particular one does not exactly fit one of the 3 identities I have, but it reminds me of one of them. So I'm going to write out here to the side, it reminds me of the identity that says 1 plus cotangent squared theta equals cosecant squared theta. And what I can do is I can take that identity and I can do algebra with it, and if I can rearrange it to somehow match what I have up above, then I can rewrite it as the other side. And so this being the case, you'll see that what we have is we have cosecant squared minus 1. If I take this identity and I subtract over the 1, then what that gives me is it gives me a new identity that says cotangent squared is equal cosecant squared minus 1. Well, this is what I've been given. And so what I've been given can reduce to cotangent squared. And so this particular problem simplifies to just cotangent squared of theta. And I'm done. Okay, on these, I will give you what I would call a non-example. In other words, this is something that you absolutely cannot do. So I'm going to put on here big old cannot do this. Okay, and this later on is going to become tempting. In other words, you'll see something like this and you'll be tempted to do this. So in other words, if I've got something like 1 plus tangent of theta, I think, oh, I've got 1 and I've got the tangent of theta. Isn't that equal to secant of theta? No, it's not equal to that, because in the formula, the trig functions must be squared. So I'm going to put on here the trig functions must be squared. Now, in this particular set of material, I'm not going to ask you to simplify 1 plus tangent, because you can't at this particular point. But you need to know for later on, in some of the problems you work, make sure you're not tempted to make this substitution when there are not squares on these problems. This concludes the lesson on Pythagorean identities for trig functions.